So now if I change the values of omega z1 or omega z2, then these values will change, but my 100k should remain 100k. So I have created one Excel sheet. All you need to do in the Excel sheet, just feed this ki formula, okay, and in separate columns have values of L, C, R1, R2, your VDD, VM. So all these values which I have put here, you can have that, and whenever you are given the specification, you will be given the switching frequency, then you, from there you can calculate omega UGB, okay, or it is quite possible that in the specification you are only given input output and you have to decide your LC, switching frequency, everything. But before you start the designing, these values should be known, whether it is given or not given. If it is not given, then you have to find out what values of LC you want to choose, what switching frequency you want to choose based on efficiency, okay, and your ripple spec and all those will be given. So based on ripple spec also you choose values of L and C. So let us see the same thing with switching. Okay. So what I did, I closed the loop. It's 50, anyway 57.4 and 57 is same. Let me remove these two. I will change the value 3.3 micro. So what I am giving? I am giving a load, switching load here. So it should settle. So you will see undershoot and overshoot based on whether your load is getting removed or applied. Okay, so 0.6 volt, beta is half, so you should get close to 1.2 volt, and this error you are getting because I am putting a 60 dB gain here. So your DC output will have some error. If I increase the gain, then it will go closer to even. So, and that error is only 2 millivolt, not less than 2 millivolt or so. So you get a little, like you see here, peaking and then undershoot. So this is mostly coming because of your, if you remember in around resonance you have that peaking, okay. If you reduce that peaking, then you can get a better response. So how can you reduce that peaking? Reduce the Q. So in order to reduce the Q, what we need to do? One way is you increase the R loss, but increasing the R loss will kill my efficiency. So another factor you had square root L over C. And if I want to keep my resonance frequency same, omega naught, because we have already calculated the values, I do not want to change my compensator. So let us say you have already designed your chip for a particular omega naught, then you do not have any option to change that, but LC is external, you can play with that. So let us say I make this L half, let me just have that 1.65 and capacitor double. So LC product will remain same, probe voltage. So I will run it and plot on the top of this. And so one benefit you should get, that your Q is reduced, so this peaking should go away or at least should reduce. And what another benefit you are going to get, if anybody remembers? No, phase margin is fine, you will get phase margin because Q is reduced. But let us say then you adjust everything, your 0, and you get the same phase margin. What about transient response? You do not remember? Transient response should improve, because your slew rate will be higher for that current. Okay, so when you change the duty cycle, your current in the inductor can change faster. Huge benefit, huh? Simply by changing L and C. So, we already know that you have a square effect because your slew rate is getting faster in inductor and you are adding more cap. So, it won't discharge that much. So, that is why just by simply changing the L and C values, it is reduced by, I mean, almost half, in less, more than half actually, and your overshoot which you were getting due to that resonance peaking, that also almost goes away. So, whenever you see this kind of behavior, then you can try to change your L and C, reduce the L and increase the C, and you can get a better settling response. Okay. So, you are settling it faster, yeah, because of this peaking, it will take more time to settle. Now, you do not have that peaking, so it is almost settled here, this guy will settle here. So, I should be able to see the similar behavior in, so this is a linear model, continuous time. When I go back to my switching model, I should be able to see the similar response. Okay, so this is my switching model. I have kept the same values. I will change these. This was, let us first do 3.3 micro and 10 micro. So, 50 ohm milliohm here and 50 milliohm I have kept here. So, total R loss is 100, and I have connected this diode to emulate the body diode. Okay. See, almost same behavior. The only thing you might see that your undershoot overshoot might be worse in this case compared to linear, because now you are working on switching model. So, you are sampling. So, you have a clock delay, from the PWM it will introduce a delay, and because of that delay your transient response will be worse compared to your what you are plotting in the linear. Okay, so this is what I was telling you guys, to create a spreadsheet in Excel, and what you feed all the values LC or KU0 from Wien, and in fact Wien and VM can be found, and if you are including beta factor then V out will matter, otherwise not. So, beta factor will only come into picture if you are using GMC compensator. So, and we did the calculation here, and the same formula I used for Ki. So, the Ki was this, okay, omega Z1 and omega Z2 you can already decide where you want to place. Omega naught and omega UGB will be known. So, LC value will give you omega naught, and switching frequency divided by 10 will give you the omega UGB. So, Ci can be calculated from there, because R1 was the feedback resistor. So, that was 100K, and then CD, your basically second zero capacitor can be calculated, RP can be calculated based on your first zero or proportional gain, and then I am adding these two poles. These are high frequency poles which are placed. So, you can see I am placing 5 times of omega UGB, H20 is nothing but omega UGB. So, now we will see why exactly we need these two poles actually. So, in order to add those two poles, what we need? We can add a series resistor here and a parallel cap here. So, this parallel cap, this will give you a pole at 1 over this cap and this resistor, because what will happen if you do not have this resistor, then what will happen at high frequency, this will get shorted. So, gain will be infinite. Now, this resistor will limit your gain, which means you are introducing a pole. So, if I do not have this, so let us say I will make it femto, means I am just removing this cap. So, I will use, and let us say I will use it few milliohms. So, you guys remember how the, so one thing you need to remember, it should not affect your loop gain, these poles, that is why we are keeping them outside UGB. It may have some effect on your phase margin, because even if you keep it 5 times away, tan inverse whatever you get from that pole divided by omega UGB, there will be some contribution because of that, maybe 5 degree or 10 degree whatever. So these two poles may cause a drop of maybe 10 degrees or so in the phase margin. So that is how you decide. So without these poles, you have to make sure that your phase margin is enough, so that after adding this pole, you still get 55 to 60 degrees kind of phase margin. Okay. So this is my, yeah, so sorry, one thing I wanted to tell you guys that if you remember, I mentioned you that it does not matter where you place the first 0, okay, your gain will automatically get adjusted if you use that particular formula, okay. So your Ki will be, so let us say I move my first 0 inside, so that will increase your proportional gain. So your UGB will be shifted, so now Ki needs to be adjusted, okay. So if you change this capacitor C1, which is integral cap, and this is also moving your 0 inside. So no matter what the value of this cap is, your proportional gain is decided by R1 and this feedback resistor, okay. So you are not basically affecting proportional gain here, and that is why if you move your 0 inside by simply changing this cap, because then it is affecting your integral gain also, so your omega UGB will not get affected. So which means I can use any cap here, okay, smaller number or higher number, as long as I keep the proportional gain same, okay. So I am using 286 picofarad here, and which is giving me probe this kind of response, okay. Now if I make it 57 picofarad, which is the original value which we had, so it will affect your this shape, but the shape after your omega naught should not get affected, or you can say that UGB should cross at the same point. Okay. So you can see here your gain is shifted up here, correct, because omega Z1 is placed at higher frequency. So which means you are placing omega A0 when gain was dropped more, but here you are placing early when gain was higher, so you needed to reduce the integral gain, and that is what is happening. Whole curve is shifted down before you place the omega Z, okay, or the first 0. But here if you see 0 dB, it remains same, and your phase margin should also be roughly same, okay. So the phase margin roughly 80K we are getting here, and if I make it to so you will get slightly higher. The why are we getting slightly higher? Because the phase contribution from this, I mean usually 90 degree you get at infinite, huh? So the lower the Z is, the phase will be more at UGB. So that is why you may get a 4 or 5 degrees, but it does not matter. So and the same thing, if you move this the second 0 at a lower frequency, your phase will be boosted, because then the phase contribution by this 0 at UGB will be more, because your separation between your UGB and that 0 is more. So, that will add more phase at UGB. So, you can improve phase margin by moving these two zeros at lower frequency, but usually the first 0 we do not want to do that. Second 0, so first 0 we have put at omega naught by 2. So, second 0 you can put at omega naught by 2, but moving that lower may not help much. Okay, I mean you may get a maybe 2 or 3 degrees, but there is a drawback with that. If I keep moving the 0 inside, that means I have to add more caps. So, area is the one problem. Other problem is the what we are doing. If you look at the mid band gain, we are reducing. So, your settling will be much slower compared to the if you place the 0 at, because I mentioned that you want your loop gain to look like more first order, but moving inside means you are getting a flat gain in between and your settling will slow down, and we can see that in simulation. If I switching, okay, so this is what I had. So, if you remember, we changed the inductor and capacitor, so we can keep the same. My settling was at 57 pico. Okay, so these are the original values, and I will run this. Okay, probe voltage. So, this is how it was looking. Now, I simply make it 286 pico. So, 286 pico means omega naught by 10, 5 times is more cap. Huh? So, that was omega naught by 2. No, curve means your omega z is shifted lower, so it will be flatter at for wider frequency range. Okay. So, what you have integrator, then first 0 will make it flat, then second 0 will rise the gain. So, in between the flat, if you move the first 0 inside, that you are expanding that region, and if you move the first 0 at closer to omega z1, then you will more be getting like a narrow kind of that band. Now, you are widening that band. So, but that is I mean overall loop gain, if you are looking, that means that will also flatten out for a wider range. That will not look like a first order system in that case. Okay. So, settling will not be good in that case, and we can look here. See. So, your undershoot will hardly get affected, but it will settle slower because of the lower gain in the mid band, because that is flat for wider range of frequencies, and that is why your settling is getting slower here. So, it is settling here, but this guy will take more time. So, if you take a 1% or so, then this might take like 500, I mean you can say like almost 100 microsecond it is taking to settle, but this guy settles within 20 microsecond or so. Okay. So, now if I want to see the, in this case, let us go back 57 pico. Let us see what is happening here. So, without those two poles, integrator, then 0, first 0, second 0, gain is rising. Now, if I increase this, So I have added first pole, and so I have added 2 poles now. Let's see what happens. Okay, so you have 3 poles and 2 0. One integrator, 2 additional pole. So it was rising. So one pole will cancel the 0, other pole will cause minus 20 dB per decade. So now if I look at the gain at 1 megahertz, here the gain is 23 dB, but here the gain is 37, close to 40 dB. So maybe 8 times, 7 to 8 times difference you can see. And what is happening at 1 megahertz? Switching frequency. So you will see a large ripple being passed by this here, and not only passed, but it's getting amplified. Okay. This is also amplifying, but the amplification is reduced. Okay. So let's say if you are getting, and we know that 1 megahertz is 10 times higher than omega UGB, so even your loop will not suppress that. Okay. If it was a lower frequency, it would have been suppressed, but it will be fully passed. So we can see the difference here. 57 pico. So I will remove these poles, and we will see what is, how much ripple we are getting here, and then we will add the pole and see what we are getting. Okay, so output is settled. Probe voltage. So this is what we are getting here. Now I will add these poles and see what happens to this. See, huge difference you can see. So why do we care about this ripple? It will not affect your duty cycle if you say. The reason is that ripple is coming at the same frequency as your PWM. So it will, your sawtooth will sample. So your sawtooth and this, so this comparator will sample. So if you compare with sawtooth your control voltage, it will always cross at the same point. It does not matter how large the ripple is. Then why do we care about this? No, this will not affect your output, because that ripple is filtered out with LC. 1 megahertz. Your LC is sitting at omega naught is very low compared to your. So everything will be filtered out. So you will hardly get a portion of that appearing. And I mean, why will you get that? That ripple is determined by your duty cycle and frequency. That is not changing. If this ripple is crossing at the same point every cycle, your duty cycle will not change, your switching frequency is same. So why would that affect your output ripple? It should not affect. VPWM is not changing due to this. Then if this VPWM is not changing, then why would it affect my, any change will happen in this power stage or output voltage? It should not happen. So why do I care about this? Okay, so let us say this is PWM is at 1 megahertz, and if I have a ripple injected in this output, at let's say 1.01 megahertz, which means 10 kilohertz higher. What would happen? 1.1 megahertz is still very high, okay. So it will get amplified and pass here, and now every cycle, if you look at 1.01 megahertz and you are sampling at 1 megahertz, so every cycle that control voltage will be changing and you will see a tone at 10 kilohertz. It's just like multiplying the two signals. If you 1 megahertz signal and take 1.01 megahertz, so what you will get? You will get those two tones and you will get a difference of the two, and difference of the two will be sitting at 10 kilohertz, and 10 kilohertz will not be suppressed by LC, but that is very low. So that should appear here, and but why would I have a 1.01 kilohertz, megahertz ripple here at the output? Harmonics of what? So no, I mean think about, you have a load here, it could be a switching load, and the switching frequency of that might be different. So that may cause a noise here, and which will get injected back, amplified and appear at the output. So let us see what happens. So what I have done here, I have a 500 milliamp fixed DC load current. So let us say some of the loads are DC, drawing DC current, some of the loads are switching, and the switching load is, so usually switching load obviously will be a digital load most likely, and that how the digital draws the current. So it will draw the current for a very short time, okay. Just take the case of inverter, during the transition only you get the current spikes, okay. So I will turn off this. So you get a very clean, good. And now if I have a simulator, let me first show you guys the current probe. So this is what I have. So I have added a current spikes which is going from 0 to 100 milliamp for a very short time, okay. So this should cause a ripple at the output, and which should be visible in your. So I am introducing that at 500 micro. So you can see here, okay, and we are getting, due to the mixing, the dominant, so we should have a 10 kilohertz. So the frequency of this I have set 1.01 megahertz. So which means this should be a 10 kilohertz. So peak to peak from here to here should be 10 kilohertz, and you can measure it. What is delta? 100 micro, which is 10 kilohertz, okay. Now this is with the pole added. Now I will remove these poles and we will see what happens. So this does not look bad compared to your output without switching load, because this is a very small ripple. But now if I do not have those poles, see, okay. and this is appearing at 10 kilohertz, and think about if you have driving this basically audio amplifier with this, 10 kilohertz is audible range, so you can listen to these tones in that case. See, so that's a significance of those two poles we are adding at high frequency. And some of this will get suppressed by the loop gain because this is appearing at low frequency. So, and your bandwidth is 100 kilohertz. So, I mean think about PSRR. So, anything below your UGB, loop will try to suppress. The same thing is here, you are having a ripple at the output at low frequency. So, it will be fed back from your loop and your loop gain will try to suppress that, and that is what is happening here. I mean if you look at that gain, we are getting 100 times, so which means this should have been order of maybe volts also, but it is not large because it will get suppressed up to some point with the loop due to the loop gain, but that suppression will depend upon your how much loop gain you have in the feedback, and but it may still appear if you do not have those poles added in your compensator. Okay. And this is, you can see here, we can measure this peak to peak. Anyway, let me delete this one. $30 millivolt. Okay. In the previous case, it was very comparable to your ripple. So, you get significant suppression by adding those poles. So, I mean we were looking roughly 8 to 10 times if you looked at the gain. So, this after adding these poles, this may be less than 5 millivolt or so, and your ripple spec usually remains 10 millivolt or less. So, as long as you have anything below that, it may not affect that much, but if you have a larger ripple, then it may affect your system. Okay.